This talk will not end today. It will end on Wednesday. So I'll write the outline for this topic. Some of this we'll do today, and we'll just continue from where we left off on Wednesday. Okay, so we want to talk about the Hubble, what's called the Hubble tension. So first we'll talk about h naught from the local distance ladder. Then we'll talk about how we get h naught from the CMB. This will be just the plan for how we're going to get h naught from the CMB. But in order to explain exactly how we do that, we'll need to track the evolution of matter and radiation perturbations. Then we'll see how we actually extract parameters from the CMB. I won't describe how the analysis is done, but we'll understand what features in the CMB depend on what parameters and exactly how we infer what we want from them. Then we'll talk about the role of baryon acoustic oscillations in this whole thing. I'm going to write there. And the last part will be putting it all together. The questions we'll ask, the first will be, what is the tension? Second question is, how robust is it? And the third and final topic will be keys, identifying keys to the solution. Okay? All right. So let's start with the first topic, which is h naught from the local distance ladder. So we defined h naught, and you probably can understand what local means, but we haven't talked about distances in cosmology, and you still don't know what the ladder means. So let's start with distances. Okay? So distances in cosmology. Let's assume a source with known intrinsic luminosity L, which is dE dt at some redshift z. What we measure is a flux F equals dE dt naught dA naught at time t naught, where this A naught is the area of a surface over which the radiation is spread. Okay, so A naught equals 4 pi A naught squared chi squared, where chi is a comoving coordinate. Note that this is the distance, this is the true distance at the time of detection or measurement. Okay? That's why A naught has to be defined this way. Okay, so now we know that dE d E naught equals A naught over A. That's just photon redshift. And we also can easily derive the time dilation exercise. I'll give you some exercise. I can't possibly do all of this even in 1.5 or 2 lectures. So once in a while, I'm going to give you little exercises which are very straightforward to fill in the gaps. Okay, so one exercise is to prove this. This is 1.5 line. Okay, so plugging these in, what we see is that the flux is given by dE dt naught dA naught, which is a squared dE a naught squared dt 4 pi a naught squared chi squared. And we can plug in the relation between the scale factor and the redshift and get from this 4 pi a naught squared chi squared 1 plus z squared. Okay? So instead of the relation f equals L over 4 pi d, which is the Euclidean relation that is also valid in on very small scales close to us, if we can measure the actual physical distance. What we get here is f equals L divided by 4 pi dl squared. Sorry, this is squared, where dl is defined as a naught chi 1 plus z. Okay, this is called the luminosity distance. All right, so we have our first distance. The next useful distance, it's not useful for this part of the talk, but it'll repeat many times today and on Wednesday, is the angular diameter distance. So if we're looking at some object with proper distance ds, and this is the angle towards it, d phi, where this object is at co-moving distance chi. Sometimes we have objects for which we know what the size is. Here we have objects for which we know what the intrinsic luminosity is. Here we have an object for which we know what the size is. The relation between these is given by at chi d phi, and we can define as dA at times chi equal to ds over d phi. Okay, so this will be the angular diameter distance to this object, where this is, I remind you, this is proper distance ds between 2 points. And from this, we see the connection between the angular diameter distance and the luminosity distance, which is given by this. Okay, now the question is how to measure H naught with supernovae. So it turns out that supernovae, specifically type 1a supernovae, are thought to be standard candles. This means that they all have the same intrinsic luminosity. Okay, so now let's expand. First, let's expand the scale factor. So just in a simple Taylor series. To first order. From this, if you take this and you divide by a, both sides of the equation, you get that z equals h naught times t minus t0. Sorry, this should be H naught. Okay? Now let's expand chi. Chi, the co-moving distance, is given by this equation, okay? Objects traveling at speed, photons traveling at speed of light. And we can expand this also. Okay. So now taking these two results together and plugging them into our equation for dl, which I just erased. So I'll write it again here. dl equals a naught 1 plus z chi. Plugging in, we get that dl equals c over h naught z plus. Okay. So therefore, if I plug this into the equation for the flux, which is what I measure, I get that the flux is equal to L over 4 pi c over h naught times z squared to this order, which means that I can get a relation between h naught and these other quantities. Okay? Now, we want to find h naught. Okay? So we have the intrinsic luminosity L here, we have redshift, and we have flux, the measured flux. Now, all we need is to measure the intrinsic luminosity L, which, as we said, for this we need to use real physical distances. And then fit for h naught using redshift flux measurements, CZ square root of f. Okay? So if we observe, once we know the luminosity, the intrinsic luminosity of supernovae, if we now look at a lot of objects, measure the redshifts and the fluxes, then we can fit for h naught. Okay. So this is done via a distance ladder. Okay? Supernovae are not that abundant that we observe them very close to us. But there are other standard candles that we do observe in large numbers, even very, very close to us, where the Euclidean approximation holds. So what do? This is the process, okay? So this is the distance, the known distance ladder. We have to calibrate. So what we do is we use a series of relations. First, we make a relation or a correlation. We measure a correlation between geometry or distances. These are real distances, physical distances, to the luminosity of some other standard candle. Here as an example, Cepheids. I'll say in a second what they are. And we calibrate the relation between these two. So distance to Cepheid luminosity. So we have some measurements. Actually, for this, there are 5 sources right now. This is done via 5 sources. 5 Cepheids. Only 5 Cepheids in the Large Magellanic Cloud, for which we can measure distances. So first, let's define what Cepheids are. Cepheids or Cepheid variables. Henrietta Leavitt discovered, I think in the 1920s or maybe 1930s, a correlation between the period of the variability of the luminosity from a Cepheid. These are types of stars, and its luminosity.
Did Hubble use that, the Cepheid variables?
Hubble also used Cepheid variables, yes.
So it probably should have been 1920s. Right?
Yeah, I think it was 1920s. So Cepheids are standard candles, okay? Because I can measure, or not I, but you can measure, or not you, but one can measure the period of variability and from that infer the luminosity of a Cepheid. If they have the same period of variability, they have the same luminosity. Okay? How do we measure the distance? The distance is measured via parallax. Do you know what parallax is? Do you know what parallax is? So what you do is you observe, so this large thing is the sun. Okay, the Earth goes around it. So the distance is 1 AU, roughly, okay, between the Earth and the sun. So what we do is we look at a star from 2 points, and we look at it against the background of very, very, very distant stars. Okay, so here there's a background of very distant stars. These stars, as we move around the sun, this image does not change. Okay, the stars are so far away that it doesn't matter where we look at them. But the way the star looks on this background, if we look from here, the star appears here versus this background. If we look from here, the star appears here. So we can measure the distance on this background image. And we know the distance is here, so we can infer this angle here. And from this angle and this distance, we can measure this distance. Okay? So that's how parallax is done, basically. And so using parallax, we measure the distance to Cepheids. We calibrate the distance to the luminosity. And then we go to the next rung in the ladder. We have to somehow tie the Cepheids to the type 1a supernovae that we can observe from very large distances. We cannot observe Cepheids which are very far from us. So we do this, we calibrate this relation. Now to do this, we need to find pairs of Cepheids in type 1a supernovae that are in the same host galaxies. Okay, so that there's not a difference in distance between them. So this is done right now using 19 sources. And from this, we get a relation between the Cepheid luminosity and the supernova luminosity. So here we have 19 such points and a line. All right, and now the last line, the last step is to take the type 1a supernovae, okay, measure their the flux from them and luminosity. And by extrapolating what we found before, we have to extrapolate. We keep extrapolating to farther and farther away distances. So now, just a second, we tie the measurements of the luminosities of type 1a supernovae to the redshift. We can measure the redshift of by looking at absorption lines in the supernovae from looking at the the light curve of the supernovae, we can see absorption lines, and from the redshift of these absorption lines, we can find the redshift of the supernovae. So this gives us a relation between the redshift and the supernova luminosity. Here, there are 300 sources. And what's important here is that these type 1a supernovae are far. So these are in distant galaxies in the expanding universe. So their motion is completely dominated by the Hubble flow. You don't need to worry about peculiar velocities contributing a lot to the redshift. So this is done with, I'm not going to draw 300 points, but this is done with 300 points. Okay, so now what have we done? We found a relation between the redshift on the y-axis here and the distance on the x-axis here, which is what we need because this is cosmologically dependent, or we can use this relation, like I explained before, to first order to infer H naught. Okay?
Why do you have only 5 Cepheid sources there and 19 Cepheid sources for the supernova?
You want as many as you can. There are only 5 Cepheids for which we can measure the distance via parallax, and there are only 19 pairs of Cepheids and supernovae which have been identified in the same galaxy. If you increase this number, you're going to decrease the error on the measurement that I'm going to tell you the result of in a second. If you increase this number, you're going to improve the measurement. Part of the reason, so this method looks complicated, but it leads to 1.9% uncertainty. And you can probably get the intuition that it's not going to be, it's not possible to improve this beyond some level of accuracy, because we're not going to get, this number is not going to go much higher, and this is a bottleneck of this calibration is a bottleneck of this whole method. So in 2019, the latest result that has been published from the Shoes collaboration.
Sources are the bottleneck and not
Sorry?
Is there a good reason why the 19?
No, they're all bottlenecks, but yeah.
I guess 5 is.
It turns out that this is the most problematic step, but and there's some hope of improving this. This you can't. I mean, you can't invent more Cepheids at the LMC. Yeah.
So I'm a bit confused because you said that there's some correlation between luminosity and variability of luminosity, and somehow you could still grow distance versus luminosity. How do you? I mean, you say that there's a correlation between two variables, and then you do a correlation.
This is the intrinsic luminosity.
And do I have any number?
But we need to know how the Cepheid luminosity behaves with distance, so we can keep extrapolating.
That's exactly what I'm asking. How do you do that? If you know
You fit a line to this relation. You measure the 5 Cepheids and you fit. For the Cepheid, luminosity as a function of distance.
But all Cepheids have the same intrinsic luminosity.
Yes.
Oh, okay. So that's
No. Well, that's not true. No, sorry. That is not true. But you don't need them to have the same intrinsic luminosity because you have the period of variability.
So I just need to assume that none of them is redshift.
Yes, that's right. But they're very close.
What's the difference between the 5 and the 19 then? The 5 you can measure.
The distance via parallax too. So you can measure exact, precise physical distances to these.
And the other 19
These are too far. You need to extrapolate this relation over to these, and then this part is fine, and then you calibrate this to this.
you calculate the distance of the 19 Cepheids from the luminosity that you measure of those 19 Cepheids. And you use a relationship from those 5 to do that.
And that's how you get the distance to the redshift of these far, far, far away objects. Exactly. Okay, so this is the ladder.
So once again, the supernova is, so for Cepheids I have this correlation between variability and luminosity, but what do I use for supernova in order to normalize?
Supernovae have the same exact luminosity.
All supernovae
Yes.
have the same.
All type 1a supernovae have the same exact luminosity. Because we assume that all of them, well, the old models were that they all are white dwarfs that passed their accreted matter beyond their Chandrasekhar mass, and then therefore it's the same exact mechanism of explosion that happens in all of them. So they all have the same exact luminosity. Well, this is debated. And if you want to attack this whole system, that's one way to go about it. But at least that's the. Okay, so this is what the shoes. Astronomers are very creative when it comes to choosing names for their collaborations and experiments. So this is called the shoes collaboration because it has the H0 here, and it's very funny. Anyway, this is what they measured. Okay, so quite precise. And I should mention that there are other ways to measure H0 sort of directly without assuming cosmology. So what you could do is you can use other calibrators instead of Cepheids. There are other types of stars for which there's some relation between the luminosity and some other factor that we can measure. And so they can be used as standard candles. And if we can then calibrate this using them, then that's another way to do this and at least increase or improve upon what the limited statistics that we have here. You can use the lensing time delay. I'm not going to talk about this at all. Of distant quasars, okay, due to gravitational lensing. If we have some object like a galaxy cluster in front of a quasar at high redshift, the light from the quasar will be deflected by the lens, which is the galaxy cluster in the foreground. And if you measure the time delay between the arrival time of different images that you measure of the quasar, that depends on the expansion rate of the universe. Okay, so this lensing time delay, that's obvious that it will depend on the expansion rate. It doesn't mean that it's easy to measure the expansion rate today by looking at lensing time delay images of distant quasars, but in principle, at least it can be done. And there are some other methods to do this. Okay.
So,
yeah.
Even let's say for the first step, the intrinsic luminosity of a Cepheid by its the variation of its luminosity to 1.9 to less than 1.9%.
No, but you have several of them.
Several what?
You have several Cepheids. You have 5 of those and 19 of these and 300 of these. And this helps you a little bit. The amount of statistics helps you a little bit.
You have to know
Yes. No, I agree. Yeah. You have to know all these things to very good precision. That's why it's already remarkable that you can reach this claimed uncertainty. Some people doubt this and think maybe this is they're under an underestimation of the uncertainty. But these people are very careful.
So how do you know the physics of the Cepheid so well that
It's not a question for me. It's a question for somebody who knows a lot more about Cepheids. But apparently the claim is that you can do this. Yeah.
And then how do you measure Z on the y-axis?
How you measure Z? So again, you look at the light curve from a supernovae and you look at absorption lines from that light curve and you measure the redshift. Okay. So let's move on to the second topic, which is H0 from the CMB. Okay. So the claim is that we can estimate H0 from measurements of the CMB, temperature, and isotropies. Let's define a useful quantity that you'll see repeating a lot today. The co-moving sound horizon at recombination or the last scattering surface. Okay, so I am not going to talk about the process of recombination. Okay, but the moment of last scattering happens when the rate of Thomson scattering of photons off of free electrons drops below the Hubble expansion rate. So yesterday we talked about interaction rates versus Hubble expansion rate. So that defines the last scattering surface, which I'm going to call the LSS from now on. So this thing we denote by RS star. So star will denote quantities at the last scattering surface in this talk. So this is given by the integral. Sorry, the star is always on the top. Okay, so this is given by this integral, okay, which is how much the light, the distance the light can travel, where this is the speed of sound. The light in the medium the light travels through. Okay, so RS is given by this formula. Now we define theta S star, which is the angular scale on the last scattering surface of this sound horizon. Okay? If I draw this, what does that mean? So this is RS star, this is theta S star. And now what's left here, we just saw the definition of the angular diameter distance, right? This is some proper distance. It's a co-moving distance. So unlike the angular diameter distance that we defined before, which was physical, and I denoted it by small d, a, here I'm going to define this, the distance here will be the co-moving angular diameter distance. Okay, so the relation is just the factor of a, or 1 plus d, between them. So now the steps to the measurement of h naught, or the extraction of h naught from the CMB, is first to measure or estimate RS star. We will see that this depends on omega m and omega b. Then we measure theta S. We will see that this is given immediately from the peaks in the power spectrum of the CMB. But I haven't said what a power spectrum is, so let me not get ahead of myself. So we measure these two quantities. Okay. If I measure this and this, I know what dA is. Okay. So now I can adjust omega lambda such that dA star equals RS star over theta S star. Okay, so dA goes as dA is this. Okay, H naught, H we saw before from the Friedmann equation, H is related to with some constant, well, it's 8 pi g over 3 divided by 3 times the sum of the rows, right? So here we have row radiation, row matter, and row lambda. Okay, so row matter and row radiation we know from the CMB. What will be missing is row lambda. Row lambda we cannot measure from the CMB well, because lambda has no influence on the CMB. It's very hard to extract this from the CMB. So, but we can adjust it so that dA equals this, because this has to be the case, right? And if we did that, then we can use the fact that dA equals this thing, and we have Hz at all z, and from that we can measure H naught. Okay? Yeah, questions?
So I understand the A part of the triangle, but I don't understand why the integral you wrote earlier for RS is perpendicular to it. Right, so this is like a size on the surface of our scattering and the distance to it.
Mhm.
Am I saying about the speed of sound in t? So speed of sound.
This is just how much a sound wave can travel
Yes. So
from the beginning to the moment of the last scattering.
and
We are measuring something that happens on a sphere, some distance from us. Okay, and that will I haven't explained yet how, but this we will be able to measure from the CMB.
0 is time 0 or today?
0 is redshift 0 here.
yeah, but for ours is
Time is not time is this is 0 time. This is the beginning of the universe, not today. This is T star. So this is from the beginning of the universe to T star, or from Z of last scattering surface all the way to infinity, which is the beginning of the universe. Okay? All right, so let me just remark that this is, of course, assuming LambdaCDM. In order to infer H naught, the expansion rate today, based on early universe measurements. Okay? So let's not fool ourselves or lie to ourselves. We are assuming that the cosmological model is understood, and it holds from the moment of last scattering all the way to us, because that's what we're basically assuming here, that we know how all of these densities evolve. Okay? But that is what's going to make this interesting, because if we don't get the same answer by extracting H naught from here, as we got from the local distance ladder, that might mean that there's something interesting. Maybe there's something we don't understand about the cosmological model. Okay, so how do we actually do this? What are the CMB anisotropies? They are a linear transformation of initial conditions. So here I'm talking about anisotropies, density anisotropies, or anisotropies in the universe at large. These are linear transformations of initial conditions, which are the metric and density perturbations delta naught that come from the initial conditions come from. Where do these fluctuations come from? Inflation, right? We talked about this yesterday. So we haven't discussed inflation at all, but that'll come. But it's not important for this talk. Okay, so the lowest order statistic is the power spectrum of primordial perturbations, which are at least nearly, if not exactly, Gaussian. Okay, so let's define the power spectrum. So the power spectrum is the Fourier transform of the correlation, the two-point correlation function. And in Fourier space, this is it. So for a Gaussian field, this is the power spectrum. This means that if we look at the variance of the correlation function, because of the relation through the Fourier transform, this is given by this. where this is an equal sign, and this is a definition of this quantity. This is a dimensionless power spectrum. Okay, so this is the dimensionless power spectrum. And what it is a variance per log interval in K. Okay? With me so far? All right, now what is a CMB map? Remember, we are measuring light, and all of it is coming from a moment, an almost instantaneous moment in the history of the universe. So we are actually measuring a sphere around us. Is that clear? Okay. So if it's a two-dimensional sphere that we're measuring around us, then if we want to expand that in some corresponding basis of functions in Fourier space, the Fourier space of this will be what? That's right. The spherical harmonics. Okay, so we expand this in spherical harmonics. So this is the spherical harmonics expansion of delta t over t in some direction. Okay, so this is the quantity we measure. We measure delta t over t. We subtract the average temperature of the CMB, divide by it for each point in space, and we have delta t over t. And that's a map. That's the map you always see for the CMB with the blue and red dots. They look like dots. You can take that map and expand it like this. And from this, you see that ALM are given by the inverse transform. And now I can define an angular power spectrum. Again, the statistic that is useful is always the two-point function because it's always Gaussian perturbations that we're looking at. But here we have a 2D sphere and not some 3D space like we have here. So here what we do is we define, sorry, I'm missing a line. Actually, I can do this here. So same way we had these delta naught of k, now we have these ALMs. And this is equal to delta LL prime, delta M prime, C sub L. That's how I denote this quantity. Okay? And I can do the same thing I just did here, which is to look at the variance of the temperature squared. And this is given by this is roughly equal to d log L plus 1 over 2 pi CL. Okay? So I'm going to leave this for you as an exercise to verify this. This is trivial. And this, we can see here that in analogy to this, this is the variance of the temperature fluctuations as a function of angular scale. Okay. Questions? All right. Now, since perturbations are small, the anisotropies are linearly related, I already wrote that, to the initial conditions. So I'm going to use that here. I'm erasing almost the exact same sentence. So L plus 1 over 2 pi CL equals d log k T LK delta naught squared k. Okay? So this gives me the relation between what I can measure. We can measure C sub L. This primordial power spectrum of fluctuations is given to us from inflation. And this what is called the transfer function, is something we need to compute. So how do we compute TLK? What gives us this relation? The first step is to solve the baryon photon fluid equations. CMB anisotropies are roughly photon temperature anisotropies at the last scattering surface. This is not entirely correct, but this is the dominant component at least. The actual photon temperature anisotropies at the last scattering surface are what we measure as the CMB anisotropies. So we need to calculate these. Okay? And then we need to convert the spatial fluctuations into angular fluctuations. All right? Questions until now? Okay. So everything up to now was easy. We are now going to delve into the calculation, and that's going to be increasingly complex. Sorry?
Spatial to angular?
Spatial to angular.
So like in Fourier transform?
Now what we're going to measure is spatial fluctuations, because we're going to use the fluid equations and measure spatial fluctuations. But those are not what we actually care about. We care about angular fluctuations, because that's what we can measure on this sphere. It's related to the question that I was asked before. What is this RS and why is it transverse to the line of sight? But we'll understand that in a second, okay? As we go along, we'll understand that, I think. Okay, so evolution of density perturbations. How much time do we have?
Another
30 minutes, okay. So we will use the Newtonian approximation and with small corrections this will be enough to capture qualitatively and even almost quantitatively what we are interested in. What we are interested in. Okay, so let's go back to the Einstein equations that we derived yesterday. Okay, and now we add, so take global Einstein equations that we derived yesterday, and now add space and time dependent velocities and density perturbations. That will be what we do now. Okay? And we start with a simplification. This whole thing is a huge simplification compared to what we actually need to do, but that takes a whole semester to explain. So the simplification we do right now is we use the ideal fluid equations. Okay. Ideal fluid equations. Non-relativistic. And no expansion. Okay? That will be the first part. No expansion. Okay, so what are the ingredients? The ingredients are, or the quantities, are the energy density, the pressure. Now these are functions of space and time. Velocities. And we're also going to add the gravitational potential. Okay, so this is the gravitational potential, because once we have anisotropies, those create gravitational potentials. All right. So what are the equations? First equation, d rho dt plus this is the continuity equation. Continuity equation. Okay. Second equation is you recognize this as the Euler equation or the Navier-Stokes equation. Okay, so this is Euler or Navier-Stokes. And then we have what other equation do we have? Yeah. Somebody said the right answer. The Poisson equation, right? Because we've added the gravitational potential. So now we need to relate the gravitational potential to all these other quantities. And that's done through the Poisson equation. Okay? And again, we have some kind of equation of state. So that's 4 equations and 4 variables. All right. So what's the simplest solution? Simplest solution is no velocities, constant gravitational potential, and constant pressure, and constant rho. Okay, so this is a homogeneous and isotropic case. No, this is all physical. We don't need co-moving because we're not expanding. There's no expansion. We're taking it slow. I'm stopping because there's a problem that I'm waiting for you to identify. Is this consistent with the equations that I just wrote? Look at this equation. So this is not consistent. And we've now identified the genes swindle. This is not a joke. You can actually Google this. There's a Wikipedia, even a Wikipedia page called the gene swindle. So apparently genes, when first deriving the gene's instability and explaining the growth of perturbations, he sort of did something forbidden like this, and it was called the gene swindle. So obviously, if we're going to take this solution as the basic solution and deviate from it now, we're doing something wrong. But this will be solved automatically when we add the expansion. Okay, so don't worry about this too much. Let's continue, even though we know that this is a wrong solution of this set of equations, because everything is going to solve itself once we add expansion. Okay, So let's now deviate from this solution. Okay? So if we deviate, we assume small velocities, small u, rho equals rho times 1 plus delta, where delta is smaller than 1. Phi equals some constant plus some deviation from it, where phi is much smaller than this constant. And now let's linearize the equations in delta, phi, and u. Okay? So there's one equation missing, which is the equation of state. And by adding that, you can see that these equations become, if I'm going slowly, you might even be able to, even while you're copying, you might be able to follow exactly how this is derived. Okay? By just plugging in those assumptions into the equations and linearizing. Now, we take the Fourier transform, so the gradient goes to, becomes a multiplication by ik, and we write these equations as okay. And from these, we get that okay. So I got this equation. While I'm erasing, check that you understand this. I'm not done though, because I've used the equation of state. I've used the Euler equation and the continuity equation, but I haven't used the Poisson equation yet. So doing the same to the Poisson equation, I will get k squared phi equals minus 4 pi g rho delta. So altogether, the equation is this, where kj is defined as this quantity, and this is called the Jeans scale. And in a second, we'll see why it's important. Okay, so this is the equation. Yeah.
What happened to the zero level?
It's here. What do you mean?
So you had rho in the Poisson's equation, you had rho val times delta. I mean, nothing changed. The rho not val. The rho val.
Yeah, no, I understand the question.
It's part of the swindle, right? Phi is first order, delta is first order.
I thought it's fine, it should be second order.
It's part of the swindle.
Uh,
Phi is really first order.
Homogeneous background should not source it by
Homogeneous isn't sourced directly. So just says, right? So
Yeah, I think you're right. It's part of the swindle. It's part of the swindle. Yeah.
You just say that anything, any question you ever get
Yeah.
in a lecture. Find a swindle.
That's right. That's right. So yeah, what I did to the Poisson equation was I missed that. I assumed this was the case. Yeah, and then derived this from that, just using the Fourier transform. You're right. This is part of the swindle. Okay, so two regimes. Large scales. On large scales, for which k is smaller than the gene scale, we define tau to be equal to cs kj squared minus k squared. And then we get the equation, this trivial equation, okay, for which the solutions are some growing mode and a decaying mode. Okay, but we know that fluctuations were small in the past and they're large today. So we ignore the decaying mode. And we take only this mode. And what is the conclusions from this? The conclusion is that at large scales, or on large scales, perturbations grow. Okay? Now this is for a very simplistic case, no expansion. We're just looking at the Newtonian approximation, but this is the same principle behind the growth of perturbations in the universe. Note that we have a competition between two quantities here. One has to do with the pressure okay, and one has to do with the gravity. So for this case, for large scales, gravity wins, or gravity dominates, and the perturbations grow. Now on small scales, so here k is larger than kj, we define omega, the dispersion relation, to be equal to this. And then we get a simple form for the equation. Okay, for which the solutions are completely obvious. It's a cosine plus a sine. Okay, this is the wave equation. So on small scales, perturbations oscillate. Okay, or pressure is able to contain gravity. Okay, now suppose that we start from no velocity, which means that b equals 0, and define the initial perturbation at t0, which is delta naught k, as a. Okay, and what we get is this form, this solution. Okay? We have until 4, right? Okay. All right. Question up to now. Okay. So now I'm going to slowly complicate things. First, let's add the expansion. Okay. We'll use co-moving coordinates or quantities. We don't have coordinates, we have wave numbers. So co-moving wave numbers k, and conformal time the eta, which is related to dt. Okay? And we're going to use the co-moving genes scale, which is kj equal to a rho 4 pi g rho over cs. Okay? So what you see here is that from the Friedman equation, this is of order ah over c. I'm going to get back to that a little later, where I used cs squared equals 1/3 c squared. Okay? If we assume that the speed of sound is dominated by the speed in photons. Okay, so now it turns out that the equations we already derived are valid for the photon number density. Okay? We'll see later that they're not valid for other stuff, but you can check that they are valid for specifically for the photon number density. Exercise. Check. Okay, so you can do this at home. And we will also get back to this, okay? We'll get back to this. Okay. So now we're gonna our perturbation is gonna be delta gamma, okay? And it's this perturbation in the number density. And assuming, again, like I did here on the right, that initially at time 0, this is 0, we get a similar looking solution. Cosine of k c eta over square root of 3. Okay? Because we're now working in eta instead of t, and I plugged in cs. Because we're talking only about photons, that's their speed of sound. Again, we denote quantities at the last scattering surface by a star. And now the redshift of the last scattering surface we assume to be 1100. The conformal time is the conformal time. Conformal time at this redshift is the conformal time at the last scattering surface, and the wave number at the last scattering surface is given by this, okay? Or I define this quantity. It's useful to define. The sound horizon, which we saw earlier, R star, is the co-moving distance traveled by a sound wave from eta equals 0 to decoupling. Decoupling is another name for last scattering surface or recombination. And this is equal to c eta star over square root of 3, which is roughly 280 megaparsec. Okay, which means that k star is roughly 0.02 inverse megaparsec. All right, so now let's draw the solutions. Okay, so these are the solutions we have. Let's draw them for different choices of k.
This is like independent of length of inflation or anything like that?
Completely, yeah, we're not discussing inflation or anything like that for now. So what I'm going to draw now is basically just the cosine in that equation as a function of the conformal time normalized to the value at last scattering. Okay? So what we get here, let me use two different colors. So this is the result for k equals k star. And this is what we get for k equals 2k star. Okay? But what we're measuring is a power spectrum. So we're actually more interested in plotting the square of this quantity. Okay? And if I plot the square of this, and this is 1, then what I get is okay, again for k equals k. Oh, I made a mistake. I meant to plot this in red. Sorry. This should be in red. Okay, so this is k equals k star. And this is k equals 2k star. Okay? If you're following me, then now instead of plotting delta of k and eta as a function of eta, I can now plot only where I'm interested in plotting, which is at the time of last scattering. Okay. Now I can plot delta eta star and k over delta naught squared as a function of k over k squared. Okay. And what I'm going to get here is something that looks like that, where this is 1, 2, 3, 4. Okay? So these are acoustic oscillations. This is what we have in the CMB. But this is just part of what we have in the CMB, because if you ever saw the power spectrum of the CMB, the angular power spectrum, it doesn't look like this. So now we need to add on additional layers of complication. Questions up to now, before I move to another feature that is important to add to this?
So what knowledge of the data is?
What knowledge of what?
Besides the time of last scattering, what else went into this calculation? Into the size of these peaks, this is just omega dark matter and omega matter.
No omega matter yet. This is just talking about the number density of photons, assuming it's just photons. We have not even added the complexity of not matter, not baryons, just expansion in a photon fluid. And we see that we have, for small scales, we have oscillations. That's it. It's very simple still. Okay?
Sorry, how does changing the number of photons on the background level affect this argument?
Sorry?
How does changing the number of photons on the background level affect this argument?
What do you mean changing them at the back
Let's say,
level?
suppose we change the temperature CMB. How does that affect this argument in the sense of, because everything you're talking about is
del T over T. Right? So
Yeah.
so how does
This is just anisotropies. There's no dependence on that, on the temperature. Here, we're just talking about only anisotropies.
Yeah, but I guess
Relative
when you
anisotropies. Doesn't
compare-
matter.
For example, when you compare it to the data,
Wait. We're very far from that. Let's okay. We're about an hour away from that. Ask me then. Okay. All right. Yes. For here, we just assumed only the component. The only component was photons. We'll talk about baryons later. I have to still add several layers of complication before I even get to baryons. Okay. They're about 45 minutes away. Okay. So damping scale. Photons can be described as an ideal fluid, like we described them, only on scales larger than their co-moving mean free path. Lambda mean free path equals 1 over A and E sigma T for Thomson scattering. On smaller scales,
There are baryons.
well, yes. Viscosity. Yes, but I haven't, but yes, there are, but only in this manner. Okay? On smaller scales, we have to add viscosity. So now in exercise, show that the Euler equation becomes gets this additional factor. So this is the drag force when velocities are non-uniform. Okay? It's fairly easy to derive. You can look at one of the references that I noted there and fill in this blank. But what we get is that the equations, instead of looking like they did before, now have this damping term. Okay, on small enough scales, this is the equation. On small enough scales. This is a more complicated differential equation, and you solve it using the WKB approximation. So you assume that delta is proportional to some exponent of I integral over eta of omega d eta. And if you plug this in, you get that omega okay, you get this relation. And so the solution now has, now this is multiplied by the exponent of minus 1/2 k squared c integral lambda m fp eta d8. Okay? now I define this as kd to the minus 2, inverse kd squared. And what I get is that the perturbations now look like the same cosine times e to the minus k squared kd squared. Maybe you need to absorb the 2 here as well. Okay. Ah, too bad I just erased that.
Why was it the co-moving mean that?
Sorry?
Why was it the co-moving mean that?
Everything is co-moving. Yes, everything is co-moving. K is always co-moving, starting from where we started with the expansion. So now, if I again look at this thing that I stupidly erased, these are the perturbations without damping. With damping, we're going to get something Of course, the dashed is what we actually, the dashed is the real thing. The solid is not the real thing. Okay, so dashed is with silk damping. This silk damping is named after Joe Silk, who is the one who first derived this. Let me write, because I did not derive this, but let me just write that perturbations are damped. You can show this in a couple of lines. On scales smaller than the characteristic scale photons can travel by random walk. Okay? And this depends on the free electron density and on rho baryon over rho gamma. Numerically, KD star is about 0.1 megaparsec, which is about 6 times K star. Okay. I have just a few minutes, so let me just talk about how to relate these to temperature anisotropies. Okay? So we found the solution at the last scattering surface, and now I want to relate these to the temperature anisotropies that we actually measure. So what we measure is delta T over T observed in some direction n, and this is delta T over T at the last scattering surface, which is at a distance given by the co-moving angular diameter distance in that direction. Okay, so we are looking towards the last scattering surface, which is at a distance dA in the direction n. Okay? This is supposed to be an eye, a human eye, observing in this direction. Okay? All right. So now, n gamma, we already saw yesterday that n gamma is proportional to T cubed, right? So this means that delta T over T equals 1/3 delta gamma. Now, what we're looking at when we're looking at an angular scale, and we're looking at some wavelength of order lambda, the relation between this delta theta and lambda is given by the angular diameter distance. And now we need to move from the three-dimensional Fourier transform to a 2D spherical harmonics transform. Right? Perturbations with angular period delta theta have a multiple L given by 2 pi over delta theta, which is also equal to K times dA star. So this is the relation between the angular multiple and the 3D wave number, co-moving wave number K, and the relation is the multiplication by the angular, co-moving angular diameter distance. 2 more lines and I'm done for today. For large L, I should say just that the angular power spectrum is the equivalent quantity to the 3D power spectrum. Okay. And for large L means large K. That's the regime in which we solved the equations to begin with. So for large L, the variance of temperature, perturbations per log L interval is L plus 1 over 2 pi C sub L. I'm losing this thing. And now I'm doing this at K equals L star over dA and KD and KD equals LD over dA. This is approximately given by the cosine squared L eta squared over square root of 3 dA star times e to the minus 2 L squared over LD squared Okay, so this is our result for today. And this was for a very simplified case where basically all we saw was that we have acoustic oscillations and we have damping. Let me just write that already from this, some features we can already derive. We know that the damping scale in 2D is given by this, and this is roughly 1500, and that the peaks are roughly at n pi square root of 3 dA divided by, or about where n is an integer. Okay, so we expect to get this, the scale, the damping scale we expect to get is of order 1500. And the distance between the peaks is of order 270 or so. Okay, this is not entirely correct. If we do the whole physics correctly, this is not exactly what we get, but this is sort of a good approximation. If you look at the power spectrum, the angular power spectrum of the CMB. On Wednesday, what we're going to do is we're going to do the matter. We're going to see how matter evolves, inside the horizon, outside the horizon, and we're going to understand how that affects the perturbations, the temperature perturbations. Then we're going to talk about the baryons, what they do, how they affect the photons, and how they're affected by the photons. And then we'll do 4 and 5 and 6. Okay?